So I wanted to make a quick video on damping and the introduction to damping, and in terms of vibrations, what a damper does and how we can include it in our solution to our differential equation. So in this picture here, I have included a mass M attached to a spring K, and now we have added a damper with a damping coefficient B. And this damper, the job of it is to dissipate energy in the system. So we have a mass that stores kinetic energy, the spring that stores potential energy, and the damper will remove energy from the system and ultimately slow the mass down if there's no external forces acting on it. In this situation that I've drawn, it's a free vibration problem. We see that there isn't any external forces here, so our right side of our differential equation is equal to 0. So what I would like to do is try to understand what our differential equation solution is going to be with this damper's presence. And the first thing to note is that when we add the damper, we have a force that depends on this damping coefficient and also the velocity of the system. So if the system weren't moving, I just pulled on it and I held it there, we're holding that system in that static position. We have provided potential energy to it. The damper is unable to access that energy in that situation because of the fact I'm just holding it. But now, as soon as I let go and the mass starts to oscillate back and forth, now the damper is starting to dissipate energy. And it ends up being that the force that the damper provides, remember that this is derived from F equals ma, the force opposes the motion and is proportional to the damping coefficient and the velocity of the mass. That's why we end up with this Bx dot here. So what we would like to do is solve the differential equation. And I'm going to make an assumption that our x of t will make an assumption that our x of t is some a e to the lambda t, where the lambda is the root to the differential equation. And the a coefficient, there will be 2 of them ultimately, are determined by initial conditions. So if we know that the position at time is 0 is x naught and the velocity at time equals 0 is v naught, we can end up finding out what those values of a are depending on the damping in the situation. In this video, we'll just go over the types of damping and not go into extreme detail. I'll reserve that for a second video. But let's learn how to solve this differential equation. I've provided x of t now, this a e to the lambda t. What we want to do is take the derivative of this assumption twice so that we can ultimately plug them in to the differential equation. So if I take the derivative of this, x dot of t will cause me to bring a lambda down. So I'll get a lambda e to the lambda t. Right, the derivative of the exponential, you pull down a factor of lambda. Since you're taking the derivative with respect to t. And if I do the second derivative, that will give me another lambda value. So with x dot and x double dot now found, we can plug them in. So I get m times a lambda squared e to the lambda t plus b, x dot was a lambda e to the lambda t, and x was a e to the lambda t is equal to 0. And if we look at all of these terms, we see that each of them has an amplitude a, which we can cancel out because we're equal to 0 on the right. And additionally, they all have an e to the lambda t. So those all cancel out as well. So we end up getting m lambda squared plus b lambda plus k is equal to 0. And our goal is to find lambda. And what we realized is that this is some quadratic equation in terms of lambda. And we can solve for lambda using the quadratic formula. And I'll just write over here the quadratic formula quickly, just in case you don't remember it. But this is the general expression for the quadratic formula when our quadratic equation has those coefficients a, b, and c. So this is kind of just on the side, because that's what we're going to do to find the values of lambda. And note that we will always have two values for x or for lambda, rather for lambda in this case. This is the one you see in high school. We'll have two values for it, x1 and x2, because of that plus or minus. Now, depending on the parameters in the system, those lambda values may both be real, they might be identical, or they might be complex conjugates of each other, and that's what we have to look at in this video. So if we're going to do the quadratic equation on this, we get that lambda 1 and 2 is going to be negative b plus or minus the square root of b squared minus 4ac, where a is m and c is k, all divided by 2a. That's what we end up getting from this. And I can write this as negative b over 2m plus or minus 1 over 2m, the square root of b squared minus 4mk. And these are my two roots. And ultimately what we would do is with those two roots is that we said originally that x of t was a e to the lambda t. So that means that one solution is some a1 e to the lambda 1t. Another solution is some a2 e to the lambda 2t. If linearly independent, again, meaning that the two solutions are not multiples of each other in some way. If they have different exponents, then we won't be able to multiply one by a number to get the other. So if they're linearly independent, the total solution is just the sum of them. That will give us a1 e to the lambda 1t plus a2 e to the lambda 2t. And that's our general expression for this, the displacement of the mass in terms of the mass, the stiffness, and the damping coefficient. But we have to look deeper than that, because depending on what the values are, we may end up with some interesting situations. And mathematically speaking, if we're looking at the results of the quadratic equation, we see we have the square root of some term, b squared minus 4mk, that depending on what those variables are, they could be positive, they can be 0, or they can be negative. And taking the square root of those different types has implications on the solution. So this thing in blue is called the discriminant, which you might have heard of in your high school algebra class. And the sign of the discriminant impacts the solution. So let's talk about this for a little bit and look at the different cases for the discriminant. And again, that discriminant is b squared minus 4mk. That's the stuff that's underneath the square root. So if b squared minus 4mk is greater than 0, so as an example, let's just say that b squared minus 4mk is equal to 9. Whatever B's, M, and K's cause that to happen, doesn't matter. Let's just assume that it's 9. That means that our equation here this would be something like negative b over 2m plus or minus the square root of 9. So we get negative b plus 3 over 2m, negative b minus 3 over 2m in this situation. Because again, this plus or minus that's here, that results in 2 different answers for lambda. And if the discriminant is positive, we end up taking the square root of some number, and we will add that number for one solution and subtract that number for the other solution. So in this situation, you see I have negative b plus 3 and negative b minus 3. These both are 2 distinct real roots. So you end up just getting real numbers. Negative b plus 3 over 2m is some number. Negative b minus 3 over 2m is some number. It's just whatever it ends up being. So those 2 numbers will go into our solution that we had before. And I just have some numbers with some exponential behavior. And it'll end up being some exponential decaying type of behavior. But in general, that is what happens if this discriminant is positive. And again, from a more physical perspective, if this b is really big and that forces the discriminant to be positive, you have a really big damper, a really high value damper, that is going to decay the motion. That's going to stop the motion as soon as it can because of the fact of removing energy out of the system. Now, again, depending on that damping coefficient relative to the mass and the stiffness, we'll see and compare how a certain situation might lead to a faster decay compared to others. But in general, the system will just exponentially decay. Exponential decay. And we will have graphs that maybe look like, maybe I give it some initial condition with some positive velocity, and it might go up, and then just going to exponentially decay. If this is the case, where the discriminant is greater than 0, we say that this is an overdamped system. It's overdamped. And again, we'll talk more about this in another video. But for now, I think it's a decent introduction. The next case is to say if b squared minus 4mk, let's say, is less than 0. So now you have a situation where that discriminant is negative. So let's say, as an example, that b squared minus 4mk is equal to negative 9. Before it was positive 9, now it's negative 9. So my roots are negative b plus or minus the square root of negative 9 over 2m. The square root of negative 9 is the square root of negative 1 times 9. And this is going to be the square root of negative 1 times the square root of 9. We get j times 3, or I times 3. But in my classes, I typically use j to avoid the confusion with current, which is I. So 3j, you get negative b plus 3j over 2m, negative b minus 3j over 2m. And if I write this out a little bit differently, where I write it like an imaginary number, we can see that these two are complex conjugates of each other. Remember, a complex conjugate is that if I give you some complex number, the complex conjugate is the same number, just with the imaginary part flipping signs. So here we see that the real part for both of them is the same. That's like this A here. And then we have the imaginary part is the same, 3 over 2m, but now you have the signs flipped. So they're complex conjugates of each other. And what's important about this is that if we're saying that the solution is some a1 e to the lambda 1t plus some a2 e to the lambda 2t, and these lambdas, these roots, are imaginary, we end up with j's, or the imaginary constant, in the exponent of those exponentials. And the interesting thing about that is that if I have e to the j with some number, this is secretly hiding sines and cosines using Euler's law, or Euler's equation. So what this means is, if you have a system with a negative discriminant, that ends up resulting mathematically in an exponential with imaginary numbers in it. And if you ever have an imaginary number in the exponential, this is hiding sines and cosines in it. And ultimately what we see is that if we have sines and cosines, we will oscillate sinusoidally. But because of the damper, what we end up seeing is that we will have exponential decay, but as it decays, the system will oscillate. That's not going to work. But if you were to look at what's called the envelope of the motion, this is the envelope, you'll see that that ends up being an exponential, and within that exponential is the actual motion that is oscillating back and forth and slowly decaying. So I have my mass, and if you're looking at me, you have the mass, it's going back and forth, and then it just slowly dying, and then stopping. But it's doing so in a sinusoidal manner. This is what we call an underdamped system. So we looked at the case where discriminants were positive, and we looked at the case when discriminants were negative. And we see that as soon as it goes negative, we now present oscillations in the system. And the boundary between those distinct behaviors is when the discriminant is equal to 0. So the boundary between having oscillations and not oscillating is when the discriminant is equal to 0. And that's the thing we're going to look at next. If we have b squared minus 4mk equal to 0, how does that impact the results of our quadratic equation? So again, let's do an example where we have negative b plus or minus the square root of that discriminant. This is negative b plus 0 over 2m. This is negative b minus 0 over 2m. And you see that when we do this, we get the same root twice. This yields repeated roots. Because of the fact that the combination of bm and k will lead to that discriminant being 0. We said before that x1, the first solution, was some a1 e to the lambda 1t, and our x2 was some a2 e to the lambda 2t. But the lambda values are the same. which means that these are linearly dependent on each other. Earlier, I mentioned that if you can multiply one of these by some constant, can you get the other? And if I were to multiply a1 e to the lambda 1t by a2 over a1, you would end up with a2 e to the lambda 1t. But since the lambdas are the same, you just get exactly x2. So these are linearly dependent on each other. And if we end up with that situation in differential equations, the way to resolve that is to include an extra factor of t in one of those solutions. I'm going to say that the total solution is going to be a1 e to the lambda 1t plus a2 t e to the lambda 2t. But again, really the lambdas are the same, so I can just leave them as lambdas if I want. They're identical. And this ends up being our solution for this type of system. In the case where we have them equal to 0, we call this critically damped. And this will decay. If we come back to the overdamped case, I'm going to copy and paste this down. This will decay similar to the overdamped case. Except it will decay much faster. So maybe it does something like this. And again, this depends specifically on the B's, M's, and the K's. But the special thing about critically damped is that critically damped decays the fastest. Compared to any other case. So at this point, we've now just shown 3 different cases depending on the discriminant, but it gets kind of complicated to figure out what's going to happen if you just know some B, M, and K value and you have to go through all this, calculate the discriminant. That's all pretty ugly. This motivates us to define what's known as the damping ratio. The damping ratio zeta. This is the Greek letter zeta. I am not the best writer, but I try to do something like that, which is kind of like a Z with a little tail at the end. That's probably not accurate at all. If you are Greek, don't be too mad at me. But the damping ratio, we're going to say, is the ratio of the damping coefficient, which is dependent on the system that we're looking at, divided by what we call the critical damping coefficient. So B crit. This B crit is the critical damping coefficient. And really what we're interested in is some reference point to determine what our values are. And the reference point we're going to use is the critically damped case when the discriminant is 0. Because for overdamped, there are an infinite number of possibilities for that as long as it's positive. The discriminant, there's an infinite number of positive numbers it can be. And similarly, if it's underdamped, there's an infinite amount of negative numbers it can be. But there is only one situation where the system is critically damped. So we define that as our reference, the thing that we're going to be comparing the damping coefficient to. And what we say is that in the damping case, or in the critically damped case, we know the discriminant is 0. I'm going to say that this is my critical damping coefficient. And depending on the M and the K of the system, we can find what that critical damping coefficient needs to be for it to be critically damped. And if you were to do some algebra, you would get 2 the square root of mk And if you do some more algebra, noting that the natural frequency is the square root of k over m, you get that this is 2m omega n. So what we do is say that zeta is defined as the damping coefficient of the system over this critical damping. You can also write 2 square root of mk, but I just wrote it like this. And we'll just write out a table to kind of summarize everything. If zeta is less than 1, that would imply that B is less than B crit. And if you're looking at this equation up here, if the B that we're actually using is smaller than B crit, that means it's smaller than 4mk, or the square of it, square root of it. And that will yield a negative discriminant. Which means that this is underdamped. And in the situation we had underdamped behaviors, we had complex conjugate roots. And what do we know about the behavior of our system if zeta is less than 1, or if we have complex conjugate roots? Because they're imaginary, the exponentials in our solution end up having imaginary parts to it, which means that we're hiding sines or cosines, and that gives us oscillations. So this oscillates while decaying. Okay. Again, that's time. That's x. Okay. The next case would be that zeta equals 1. Well, if this is equal to 1, that means that B is equal to the critical damping coefficient, which means it's critically damped. B equals B crit. This has a 0 discriminant. This is going to be critically damped. And as we saw before, in our quadratic equation, we had negative B plus or minus 0 over 2m, and that led to repeated roots. And what we saw is some sort of exponential decay. So perhaps, maybe it looks something like this. It depends what the initial conditions are. Before I drew it like this, that was just due to these initial conditions. You could also have it where maybe the initial conditions are negative, but it'll eventually just die out to 0 exponentially. And then the last one is zeta is greater than 1. In this situation, that means that B is bigger than B crit. And if B is bigger than B crit, we know that that expression, the discriminant, is going to be positive. In that situation, we call that overdamped. And these are going to be 2 real distinct roots. And it'll look very similar to the critically damped case, except now it'll take a little bit longer to decay. Something like that. And that's our introduction to damping. Just to summarize, what we did was look at the solution to the differential equation using the quadratic formula. And the thing that has a huge impact mathematically and also physically is the b squared minus 4mk underneath the square root. Because in our solutions for lambda, depending on the sign of that discriminant, that has a huge impact on lambda, and lambda has a huge impact on the solution to the differential equation. So we looked at the three cases where the discriminant is positive. We saw that we ended up with these two real roots that were different from one another, and we end up with some sort of exponential decay that occurs. In the situation that it was negative, we saw that inside the square root, we have a negative number, which leads to imaginary terms popping out. In that situation, they ended up being complex conjugates. And because of Euler's equation, we know that an exponential with imaginary numbers is actually hiding cosines and sines in it, which implies that our system will oscillate sinusoidally and it will decay while doing so. And then the third case, which was the reference point for us, is the critically damped case, where the discriminant is equal to 0. It's kind of the portal between the positive and the negative discriminants. It's a very special case, which is why it is used as a reference when we define the damping ratio zeta. And we see that zeta, depending what its value is relative to 1, will dictate the behavior of the system. And just to come back up and ensure we understand the critically damped case, we end up with repeated roots. And if we have repeated roots, we have to make sure that the solutions are linearly independent of one another, which is why we're motivated to add this extra factor of t into one of the solutions. It doesn't matter which one, because the A1 and A2 are arbitrary. It depends on initial conditions. You'll solve for them as is, and then your solution will always work. And the critically damped case is a lot like overdamped, except it will do so more rapidly. It will decay more quickly compared to the overdamped case. I know this video probably went on longer than I was originally expecting, but there's a lot of material here. So I hope that this helps with the introduction to damping. I will make another video going over the critically damped case and the underdamped case. Overdamped gets a little bit too algebraic, but we'll focus on those others in future videos. I hope this was helpful. Please let me know if you have any questions. Okay, thanks. Bye.